1911, a self-taught genius from India named Srinivasa Ramanujan posted a problem in the Journal of the Indian Mathematical Society. He waited 6 months. Not a single person, not even the top mathematicians of the era, responded with a solution. Looking at it, you can see why. This problem here, the infinite nest of square roots. Most people look at this and see the numbers 2, 3, 4, and it grows forever and assume the whole thing must explode to infinity. But Ramanujan knew that infinity often hides a very simple secret. So today we're going to peel this onion layer by layer. So how do we approach this nested radical? To solve this, we don't start with a problem. We start with a simple identity. Consider a function f of x is equal to x plus 1. Well, we know that any positive number is the square root of its own square. So we know that x plus 1 is equal to square root of x plus 1 squared. If we expand the term inside the root, we will get x plus 1 is equal to square root of x squared plus 2x plus 1. Now, let's rewrite x squared plus 2x by factoring out an x. This will give us 1 plus x times x plus 2. This is our seed. It tells us that any number plus 1 can be written as the root of 1 plus that number times itself plus 2. Now step 2 is going to be the recursive substitution. And this is the portion where the genius of Ramanujan kicks in. We have an expression for x plus 1, but we also have a term x plus 2 sitting at the end. We can use our seed formula to rewrite x plus 2 as well. If we replace x with x plus 1 in our original formula, then we'll get that x plus 1 equals to the square root of 1 plus x plus 1 times x plus 1 plus 2. Which simplifies to x plus 2 is equal to square root of 1 plus x plus 1 times x plus 3. Now we take this new expression for x plus 2 and plug it back into our first equation and look at what happens. X plus 1 will equal to square root of 1 plus x times square root of 1 plus x plus 1 times x plus 3. Now we push to infinity. We can do this again and again. We can substitute x plus 3 using the same rule. And then we will get that x plus 3 is equal to square root of 1 plus x plus 2 times x plus 4. Now our main equation will grow another layer. X plus 1 is equal to the square root of 1 plus x times square root of 1 plus x plus 1 square root of 1 plus x plus 2 times x plus 4. So then we are given this big nested radical here. If we repeat this process infinitely, you generate the exact structure of Ramanujan's problem. The multipliers become x, x plus 1, then x plus 2, and so on. So now we can solve for a specific case. Now, look at the original puzzle. It starts with the number 2 as the same multiplier outside the second root. So, in our formula, the first multiplier is x. So to solve Ramanujan's specific problem, we can set x equals to 2. And then, if x equals to 2, then the left side of our equation is 2 plus 1 equals to 3. And the right-hand side becomes square root of 1 plus 2 times square root of 1 plus 3 times 1 plus to infinity. And there it is. The infinite chaotic mess of roots is actually just a very long, very complicated way of writing number 3. Meaning that we'll have the answer to this problem here will become 3. Ramanujan proved that as these roots go deeper, the tail of the sequence grows so slowly compared to the square roots that it effectively vanishes. It's a minimal problem with a massive legacy. If you want to see more math than looks like magic, hit subscribe, and I'll see you in the next one.